Dear colleagues, dear friends, thank you very much, the organizers, for inviting me for this nice meeting and for awarding this honorous George Zaslavsky Award. So in my talk, I will speak about populations of oscillators as a complex benchmark, and I will span topics from integrability to disorder. Synchronization is an old phenomenon, and more than 350 years ago, Christian Huygens first observed synchronization of pendulum clocks, and he already explained that this synchronization, this phenomenon, is due to interaction of these clocks, however small it is. In 19th century, Lord Rayleigh described synchronization of organ pipes. I don't have picture of organ pipes from 19th century, but these are experiments which were repeated by different groups and also in Potsdam by a group of Marcus Abel. And the more modern development in the studies of synchronization started with works of Appleton and van der Pol, who observed synchronization of electronic generators. The universal tool, which is now widely adopted for description of synchronization phenomena, is the phase reduction. Indeed, if an individual system has a stable limit cycle on which the dynamics is periodic with some period t, one can parameterize this limit cycle by the phase which changes from 0 to 2 pi. And moreover, this parameterization can be extended to the basin of attraction of the limit cycle. So in this vicinity of the limit cycle, there is a variable phase which grows uniformly in time proportional to the frequency. And then interaction of oscillators results in adding some interacting terms which also can be represented through the phases. And for the first time, this was done by Robert Adler in 1944. He derived this equation for the phase difference of two coupled oscillators. So delta phi is phase difference, and on the right-hand side, which is very simple, there are only two parameters. So the frequency mismatch between the natural frequencies of two oscillators and the coupling strength epsilon. And if this coupling strength is strong enough, so the frequencies become, observed frequencies of the oscillators become identical, and the phase difference is a constant. It's, by the way, so maybe not everybody knows this scientist, Robert Adler. When he died in 2007, even in German newspapers, there were articles about him. Of course, not because of this equation. He did a more prominent contribution to our everyday life because in 1953, he invented the remote control unit for television sets. So all the remote control units which we are used now are due to Robert Adler. So this was about two oscillators, but there are situations when there are many oscillators. And let us first consider a situation where they are globally coupled. It means that there is some medium through which these oscillators interact. So if we have metronomes like here, so then the common platform makes them interacting. Pedestrians on a bridge can also synchronize due to movements of the bridge. Arrays of electronic oscillators or Josephson junctions, they can have common load. And this picture to the right shows a spectacular experiment with more than 2 million of cells where genetic clocks are introduced. They are now biopixels, which with some period about 90 minutes, and one can observe how these biopixels synchronize due to interaction via some chemicals in the surrounding medium. So this is how it looks for metronomes. So this is video made in Potsdam, and you will see Markus Abel and Michael Rosenblum who are preparing this experiment.
Ist und dann legen wir 2 Kaffeedosen runter, so dass wir rollen können und dann.
And so you initiate metronomes randomly. And after some time, so they demonstrate synchrony, not all of them, so some are out of phase, but majority is in phase, and they have the same frequency and the same phase. Now, if you, this is a famous video from the opening of the Millennium Bridge. Due to interaction of pedestrians, you can consider walking as a periodic process. It's a limit cycle, but interacting with the bridge, so there is a transition to collective synchrony where bridge oscillates and also pedestrians on the bridge oscillate in takt with this bridge oscillations. Here you can see how this oscillation is. Okay, so let us proceed to the theoretical description of these globally coupled oscillators. So the picture looks like this. So you have many oscillators, say N, and you combine observations in some common field, global field, which acts then on each of these oscillators. So X is a common load for electronic oscillators, say, or a platform for metronomes. And the equations for one oscillator you extend to the action of the mean field, where epsilon is the parameter which describes the strength of this action, and the mean field is sum of over all oscillators. And in the phase reduction, you reduce the equation for each oscillator to the phase dynamics, and this phase enters then the mean fields. So all possible mean fields can be represented through this Kuramoto Dida order parameters. So the mean fields, so the moments of the phase distribution, complex moments of the phase distribution, and the equations now look like this. So that there are mean fields, and each oscillator is driven by these mean fields. And this function, if you think about also apply some averaging, only such combinations can appear which are slow variables. And if you keep only the simplest such combination, you come to the famous Kuramoto model, which reads like this. So it's formulated for phase equations. So there is natural frequency omega k, there is coupling strength, and the action is through this order parameter. You can rewrite it, and you see it is more or less equivalent or exactly equivalent to the interactions where sine is the coupling function. So it means that it is a direct generalization of the Adler equation, where also two oscillators interact via this coupling term. By the way, so I strongly recommend maybe you have a look at this video by Yoshiki Kuramoto. He prepared it just remembering how he created this model, solved it, and presented it at some scientific meeting. So how Kuramoto solved this model? So he used the approach from the statistical physics, where you define an equation, a self-consistent equation for the probability distribution of the phases. So it is like one does in the Weist theory of magnetization, where you assume there is some magnetization, then you find the distribution of your elementary magnetic moments and define the total magnetization from the self-consistent equation. And the same you do here for the complex order parameter Z1, which plays the role of macroscopic magnetic moment, and especially for some particular distribution, Cauchy distribution of frequencies, Kuramoto was able to calculate this self-consistency condition, some integrals exactly, so that you have exact formula for the complex order parameter beyond the threshold, and synchronization happens as a non-equilibrium phase transition when coupling parameter epsilon exceeds this critical value, which is proportional to the width of the distribution of the natural frequencies. Now, let us do a little bit more than Kuramoto did. So let us try to find time-dependent dynamics of the order parameters and of the phases. So here we suppose write some generic form so that it will be applicable not only to the Kuramoto model, but to the whole class of models, including Josephson junctions and theta neurons, so-called, and many others. So you write equations in this form, and in particular case, when this H is just proportional to the Kuramoto order parameter, you obtain the Kuramoto model. But this is equation for the phases. So for the moment, we assume all frequencies are equal. So in the thermodynamic limit, when the population is very large, you can describe it with a distribution density. And for this distribution density, you write the kinetic equation. So it looks like a linear equation, but these terms in this equation, they depend on H, and H depends on moments, and this moment is the integral of P. So it is a complex, nonlinear, partial differential and integral equation. But the simple situation is because the phases are variables on a circle, so you can represent P as through its Fourier modes. And you, instead of such a partial differential equation, you can write a system of equation for the Fourier modes. So it is infinite system, modes are coupled to each other, it is infinite, all n larger than 1 should be taken into account, and because H can potentially depend on this Z1 and some other order parameters, this is a nonlinear system. Now, before proceeding, so let us generalize. Let us include noise, because in many cases, noise a little bit simplifies the dynamics, so it looks like something damping, and it's exactly this case for the kinetic equation. So if one considers noise as a Gaussian and white noise, so then one can write the Fokker-Planck equation instead of the Liouville equation, so that additional second derivative diffusive term appears, which is proportional to the noise strength. And this infinite system of equation for the modes gets an additional term, which is proportional to the noise intensity. Now, but below we also consider Cauchy noise, Cauchy white noise, which might be not so good for usual variables, but on the circle, so you don't have problem of the tails. So Cauchy noise looks not very much different from Gaussian noise. It also gives some damping, but a little bit differently. So there is a fractional Fokker-Planck equation with this term, and in the Fourier space, you get decay of the modes, but with some other coefficient differently to the decay or the white noise. So it's interesting that Cauchy noise and Cauchy distribution of frequencies are very much similar. What it means Cauchy distribution of the frequencies? Now frequencies are different, so you put here some deviation from the natural frequency. Now this psi is not time dependent, it is not noise, but it is some constant. So all frequencies are different, and their distribution you take in the form of the Cauchy distribution. Now it is a problem becomes more involved because so you have to write this corresponding Liouville equation, kinetic equation for each particular psi. So psi is now parameter in the density. You write this equation for some particular psi. And in averaging, you have also an integral over all psi's. And this existence, such an integral, gives you an idea, so why Cauchy distribution is so natural to consider here. Because then the integral can be potentially calculated through the residuum theorem. So you take this integral, assuming that this function of psi is analytic in the upper half plane, and then calculation of this integral with such a factor gives you a value at the pole psi equal to I, and you from the set of differential equation, you come back to just one equation for the Fourier modes of this distribution. Now I summarize all three cases here in this slide. So Cauchy-Lorentz distribution of natural frequencies, equation looks like this, and the damping term is here. Cauchy white noise, equation looks like this, and Gaussian white noise, you have damping term, which is here in this notation proportional to n. And remarkably, these two cases lead exactly to the same equation. So Cauchy noise or Cauchy static distribution give the same result. So it is these equations which we will study in more details just below, because we will see the integrable and then we will return back to the Gaussian white noise. So this is an infinite system of equations. H can potentially depend on Z, but you write it in very generic terms. So this is some time-dependent complex field. Omega potentially can be also time-dependent. And this is infinite dimensional, but there are two remarkable finite dimensional reductions. The first one is due to Watanabe and Strogatz. Watanabe at that time was a PhD student of Steve Strogatz, and unfortunately I haven't found his photo in the internet. So, but in these two remarkable papers 30 years ago, they have shown that in the noiseless limit, gamma equal to 0, so you can reduce the system to 3 real variables and a constant function which depends on the initial conditions. So it is some kind of partial integrability, but it is valid only in the so-called conservative case without damping. Now, another substantial progress was done in 2008 by Edward and Thomas Antonsen. They realized so that this infinite system of equations can be reduced to one complex variable or two real variables if you assume that such condition holds, so that higher order moments of the distribution are just powers of the first moment. And this is the property of the wrapped Cauchy distribution. So, so this case defines so-called Antonsen manifold. I put it schematically in this picture. So Kuramoto quite early found a fixed point solution. Now, Ott and Antonsen they found a particular manifold where the distribution of the phases is the Cauchy distribution, and it remains as Cauchy distribution. Also, its parameter can change. But it is only one invariant manifold in the space of all possible distributions. But on this Antonsen manifold, you reduce the equation just to one equation for the main order parameter, or in the case of the Kuramoto model, you get exactly this equation, and you can solve it. You can do many different things with this equation, consider two populations, and so on. Now, what was our contribution to this field? So we, with Rok-Chesnik, postdoc in our group, found a complete finite dimensional reduction. It means, so this, what I write here, without derivation, because it is rather lengthy, is valid not only on the Antonsen manifold, but everywhere in the phase space. So there are three complex variables which obey these equations, and there is one constant function, m, also complex, and which doesn't depend on time. And this solves this infinite system with arbitrary initial conditions. So the moments, circular moments of the distribution are defined through this function and three variables, q, y, s, through this, rather complex series, but there are explicit formulas. For example, the first order parameter is just this expression. And this is exact. So you can say, so you put any initial distribution of the phases, you need to specify initial conditions to the system. We gave a recipe how to do this. So our suggestion was to put these variables in this way. And so this constant function is nothing else as a characteristic function of the system of moments at time zero. So it is some transformation of the initial distribution of the phases. And for example, for some interesting distribution, if you have finite number of these moments, you will have a polynomial. And so this is how the problem is solved. Now, let us relate this exact solution to the previous cases of Watanabe-Strogatz and Antonsen. Now, in the case where gamma is non-zero, we can show here analytically that this variable y decays in time. So it is strictly less than some negative value, which is proportional to gamma. It decays in time, and y equal to 0 means so that we are remaining equation is for q, and this is the Antonsen manifold exactly. So we show here how the system approaches this Antonsen manifold, which is the global attractor. But you need dissipation. You need gamma larger than 0. If gamma is equal to 0, you can modify this equation, so play a little bit, and you reduce this system to that of Watanabe-Strogatz. So this means so that this solution combines these two previous approaches. So numerical illustration, we did it for some system of Josephson junctions because they have more non-trivial dynamics than just Kuramoto system. So this is illustration of how you converge to the Antonsen manifold. So this is how this variable y decreases in the case if you have gamma non-zero, but it doesn't decrease if gamma is 0. So decrease of this variable means that exponential decrease, that you exponentially approach Antonsen manifold. Also, you can compare, so if this rather complex analytic reduction is valid for some ensemble, so you take 10,000 units, calculate moments, and compare with equations for these moments, and you see perfect overlap of rather involved dynamics here. Now, why this approach, where it can be useful especially? Now, in many cases, you can just enough to consider Antonsen equations because you are attracted to them. But here, our approach also allows to find transients. So how you approach to Antonsen manifold. And especially it is interesting if there are several attractors or say multi-stability on the Antonsen manifold. So, for example, in many situations, synchronous and asynchronous states can coexist. And then the question is, so where I will come if I perturb my state, I make some kick, I change the distribution of the phases, I go away from the Antonsen manifold, and where I will come back, either to the same attractor or maybe to another one, and this depends on the Bayesian boundary between these two attractors. And this Bayesian boundary can only be obtained by our approach because Antonsen equations are valid only here and not outside. So we did such experiments. We had a situation where there is a bistability between asynchrony and synchrony, and you make some kick, you perturb the system, and you go either to another attractor if the kick is large enough and you are inside of this, say, balloon, or you return back to the same attractor where you started if your perturbation is small, and this is the white domain. And indeed, in many cases, you need such a perturbation. Okay, so let us conclude this first part of my talk. So I showed that there exists exact low-dimensional reduction for a population of oscillators. There are not very generic case, so coupling should be first harmonic, Cauchy white noise or Cauchy distribution of natural frequencies and thermodynamic limit. And this reduction also means so that the system is partially integrable because you have one constant function which you define from initial conditions and it doesn't change in time. Okay, if one has an integrable system, so then the idea quite often is, so you have the case which you can solve, maybe you can construct a perturbation theory close to such a case. And indeed, this can be done if you have a Gaussian white noise. Not Cauchy noise, but Gaussian white noise. Now I take the same equations as before, but now I put here additional term Gaussian white noise. Now it is proportional to n, and therefore it doesn't satisfy. So this, you see here, right-hand side doesn't depend on the index n. Now you have n dependence. And so the Antonsen manifold and this reduction exist only if sigma equals 0. But can we maybe make a perturbation close to this case? And this is indeed possible, and especially nice, this perturbation theory is formulated in terms of circular cumulants. You know, there are cumulants in the probability theory which are especially simple for the Gaussian distribution. And here we have a distribution on the circle, and the especially simple is the wrapped Cauchy distribution. But you can introduce circular cumulants. Now they are complex, and they are related to the circular moments, just as normal cumulants are related to the normal moments. It's the same expressions, and these cumulants have a nice property. So on the Antonsen manifold, for which we want to construct the perturbation theory, only the first cumulant is non-zero, but all other cumulants vanish. And this allows for nice formulation of the perturbation theory. So if you have small term, you expect that cumulants, which are larger than 1, will be small. And moreover, you can have a hierarchy of them so that the larger the index, the smaller the cumulants. Now sigma square is small parameter. And you truncate this infinite system just by two equations. So you make a small error. You consider only the leading and the second cumulants. And you, for the third cumulant, you have some choice of how to express it, but they are more or less the same. And as a result, it is approximate system for two cumulants, which is close to Antonsen manifold and allows for a description of system with noise. So this, we compare here, so this perturbation theory based on cumulants with just the Antonsen ansatz and the Gaussian ensemble approximation, Gaussian ansatz. And you see, so these black lines, here it is error in the theory, so how you describe the moments. And this error is indeed very small for small noise, but even for rather large noise, it is definitely smaller than, say, Antonsen ansatz. And here it's Gaussian might be better because noise is very strong. But for small noise, you have several order of magnitudes improvement through this perturbation theory. Now, I conclude this part mentioning that you can extend, make a perturbation close to the Antonsen manifold using the integrability, which was established, and the approach is not exact in the thermodynamic limit, but as a result, you reduce infinite dimension system to just two complex equations. We started with a global coupling of oscillators where we have some kind of common force, some load or platform. But in many cases, so that you don't have such a configuration, but instead you have a network of all-to-all pairwise couplings. And for example, if you consider blinking fireflies, which is also a classical example of the synchrony in large population of oscillators, there is no medium which makes interaction, just each firefly experience light from other fireflies. And so there is a just propagation of signal like in this picture here above. Now, let us generally speak. So we have seen that Kuramoto model can be formulated also in this way, but in many cases, one assumes so that all interactions are the same. So you have more or less identical elements at each side, and your couplings are also all the same. And this means so that you have just unique function f, which describes coupling, and so only difference of phases matters. Maybe oscillators are a little bit different due to their frequencies. But in more generic setting, you can have very different oscillators, and you can have a coupling matrix, which is also not, all links are not identical, but there are strong links, there are weak links, and these links can also include some kind of delays. And in this case, you still can describe each oscillator as a phase oscillator, but you cannot expect that couplings will be all the same. There could be different functions, and for each pair, you have its own function. Moreover, so this function can be chosen randomly. So we gave with our paper with Lev Smirnov, which I mentioned, a sample recipe for averaging random coupling functions. So we derived it, but here I don't have time to do this. So the idea is very simple, or the recipe is very simple. If you have such a coupling function, such different random coupling functions, you just replace it with an average coupling function where you average over this ensemble of these functions. So in the most simple particular case, so you have different strengths of coupling for different pairs, and you have different phase shifts here. Phase shifts may come, for example, from the delay in the coupling. And so you have some distribution of these two parameters, strength of coupling and phase shift of coupling. Phase shift of coupling is a circular distribution. And then your average coupling function is just here you average the strength, and extra you average over these phase shifts. And this is nothing else as a convolution. You see, you have convolution of your function f and the distribution of phase shifts. And in the Fourier space, it means so that modes of this function are and function j are multiplied. So you can only get something simpler due to this convolution than the original function. And we use this in this numerical example. So we consider an ensemble with noise and with a function, coupling function, which contains two harmonics. And here the transition is quite involved. So if you change your parameter strength of the noise, so without phase shift, so no alpha, you have first the second harmonic appears, and then the first harmonic appears at quite large noise terms already, and they somehow involved, distribution is rather involved. But if you make a convolution with a function which has only the first harmonics, then the second harmonics is killed in this function and also remains the first harmonics for which you have an analytic solution. And indeed, with phase shifts, you see, so this is numerics and this green curve is analytics. You see so that you reduce your coupling to the first harmonics, and it is described by the analytics theory. Okay, so conclusion here is so that if you have random couplings, and randomness can be in many elements, the recipe is just to average, and this should work if n is large enough. And moreover, in more complex situations where you don't have Kuramoto type coupling, but what is called beam-free type coupling, where this is instead of function, you have a product of two functions, you can also average them and have such a product of average functions, and it will describe your ensemble. I am coming to the last part of my talk. It's our recent paper with Franco Bagnoli. It's the same model which was before with random phase shifts. And now I take for this phase shifts a uniform distribution. So they're completely random and uniformly distributed from 0 to 2 pi. So if I will apply the recipe from the previous part, this averaging will give you just 0 because of this uniform distribution. And you can ask a question, is there still something in this model? So averaging says so that there is no synchronization transition, but maybe we have lost something while averaging. Okay, let us consider more carefully and notice here that I don't normalize this coupling by n because there will be some other generalization. Normalization will be later. So the usual order parameter, if you calculate for this system, which says so it's like magnetization, we will see below in the numerics that it is always very close to 0. So there is no synchronization in the usual sense, so that there is no collective order in the system measured by this parameter. But let us make a more fine-tuning characterization. Let us look on pairs of phases and include also in this pairs phase shift and calculate this sum. So this is some kind of averaging over all connections and the averaging of this quantity over all elements. So there is some complex, let us call it correlation order parameter, because it involves these phases, phase shifts. And if there is no phase shift, so these two parameters are related to each other. So this Kuramoto order parameter and this correlation order parameter, which is then real, so they're just almost the same. And let us take the real part of this new order parameter as a measure of some kind of correlations. And also, the second measure, we will calculate the observed frequency of the elements. And look what is happening if we increase coupling F. And this is what you have for the standard Kuramoto model. So in the standard Kuramoto model, these are frequencies, and this is the order parameter. So here it is not zero because of finite size fluctuations, but there is a transition here. And you see, so nothing happened to frequencies, but here frequencies start to come close to each other exactly at this point of the transition. And the transition is at some coupling constant, which is non-zero, so there is a threshold. So if I will take here many more oscillators, it will be just a perfect transition curve predicted by the Kuramoto. But let us now take our disordered system, and we look on this correlation order parameter, and we see that for different system sizes, 100 up to 800, so there are this growing and saturation. And moreover, you can rescale these curves into just one curve, so that this correlation order parameter depends, so this is a universal function, where n, you see, comes in power 1/2, and here it is also in power 1/2. So correlation appears reliably, and there is no threshold. So immediately, starting with small coupling, you start to see some synchrony, some correlation in this completely disordered population. And here, it's values of the usual order parameter, and you can see so that it is here, it is very small, it is just finite size effects, because for larger number of elements, it becomes smaller, so it is more or less like this. Now, let us look at the frequencies, and here there is a remarkable observation. Frequencies, for observing frequencies, you don't need to know phase shifts. You have just to observe your oscillators. And you see, almost immediately after introducing coupling, the frequencies are moving together. This is just one realization. And there is some place where they are really together, so close to each other, and then they become to diverge for large couplings. And if you make an averaging, so you see that standard deviation of the frequencies reduces by some visible factor. So from 1, it goes to 1/4. So factor 4 here for 800 oscillators, and then it starts to grow again. So you see, so it's indeed, although you have complete disorder, you see some elements of the order in this, of some synchrony in this population. So you also see this correlation order parameter for noisy oscillators. It's very similar scaling as before. So conclusion here is that although you have a very random phase shifts, so all the interactions are completely frustrated. But there is a specific correlation order parameter that shows transition to synchrony, although the synchrony is quite small. You see here this factor size of the ensemble enters, and especially so the frequencies become closer to each other due to interaction, even you have completely different phase shifts. So it's almost all I wanted to say. So there are many other interesting things in the oscillator populations, like self-organized quasi-periodicity. You can synchronize chaotic oscillators. There are interesting chimera states where some oscillators are synchronized, other asynchronous. You can have cases where phase synchrony is related to frequency anti-entrainment. So many other interesting features, but I have restricted time. And at this point, I end and thank you for your attention.